Why can some light cross billions of light years while ordinary waves fade after a few meters? In the energy filament theory, the answer is that light is a very specific rhythm launched into a narrow channel of the energy sea, guided by long tension corridors and continuously refueled at the source. So the real limit is not whether the pattern can survive the trip, but how much of it your tiny patch of sky still receives. Our everyday sense of waves comes from pawns and echoes. Drop a stone in water and the ripples spread out in rings until they flatten, shouting across a field, and the sound thins out until it disappears. So it feels obvious that any disturbance should quickly smear out and die. In this picture, the universe is already filled everywhere with a tense, elastic energy sea. Light is not a lump thrown into empty space but a repeated tighten-release dance passed along from place to place. And as long as nothing keeps stealing too much of that motion, the relay itself does not decide to stop. The subtle part is how that dance is launched. Around every stable particle there is a tiny near-field structure, a swirling-like pattern that locks the particles into a few allowed orientations. When an electron drops from a higher energy state to a lower one, it has a piece of extra energy to give back to the sea, and it cannot spit that energy out in any random direction. It has to use the open slots already carved into that swirl. Those slots act like nozzles that pre-select a very thin set of directions for the outgoing disturbance. So by the time the light pattern is born, it is already squeezed into a narrow cone, instead of exploding evenly like a perfect sphere. Once the pattern is out in the wider sea, it keeps stepping forward along that cone. If nothing absorbs it or scatters it too much, the same basic rhythm is handed on and on. So the question of whether it can get here is almost always answered with yes. What really changes with distance is how thinly that pattern is spread by the time it reaches your detector. A household bulb has very little energy to spend and has to throw it out across almost the whole sky. Close to the bulb, your eye or camera still sits inside a cone that carries a decent share of its total output. But as you move away, the same cone contains less and less of what the bulb can afford to send. Very quickly, the amount of rhythm that arrives in that tiny slice becomes too small for your sensors to pick out from background noise. So you concluded that the light could not travel very far. When in this view, it is more precise to say that you no longer get a big enough share to notice. A star plays the same game with a completely different budget. Inside a star, a ridiculous number of electrons are constantly stepping down in energy, and every step has to push excess energy out through the swirling patterns wrapped around those particles. For the tiny set of directions that happen to line up with Earth, this means there is a steady torrent of little pushes being injected into the same narrow corridor of the energy sea. Even after that corridor stretches over billions of light years, the portion that lies inside the narrow cone that hits your telescope still carries enough of the star's total rhythm for us to detect, count, and even split into spectra. There is one more ingredient: the quality of the corridor itself. The energy sea is not perfectly uniform. In some directions, its tension and texture line up in a way that makes it easier for a disturbance to stay focused, a bit like laying a smooth highway through the landscape, while other directions are more like slogging through mountains and forests where the pattern is more likely to be scattered or absorbed. Near black holes, the tension field can become so extreme that it creates genuine corridors, long narrow regions where motion is strongly guided. In later seasons, we'll talk about how black hole jets behave almost like cosmic fiber optic cables, where matter and light crammed into these corridors can shoot out for hundreds of thousands of light years. Ordinary space is much gentler, but the same logic holds. Some paths through the sea act more like well-paved lanes, helping the light pattern keeps its shape and direction for a very long run. Put all of this together and light traveling very far stops being a mystical property of a particle that never decays and becomes the natural outcome of three concrete pieces. First, the direction of emissions is already narrowed at the swirl pattern gate when the light is created. Second, the energy sea along some directions provides long-distance tension corridors that can guide the disturbance without tearing it apart. Third, the source keeps stuffing the same rhythmic pattern into that corridor over and over. So that even after immense spreading, your tiny patch of sky still gets a faint but readable share. Tap follow, share it on New Physics, Clear Universe.